Is everyone here? I think.
Feels like there should be a bit more. Who else not here? Yeah, maybe everyone's here. Yeah, may do a quick check in the Telegram. Check what.
I think Wei Lin and Jackie not here.
Oh yeah.
But it's recorded lah, so I think it's okay if they want to. Okay, I think can start already. Yeah. Okay, sorry for the delay. So this is the second Learn2Learn session, and our group, which consists of Alissa and me, will be presenting group theory in cryptography. So a basic introduction on what are we going to talk about. First, we're going to talk about the basics of the groups, including some introduction, the axioms, and some terminology like the finite group, the subgroup, the homomorphism, ring fields, and all the stuff. And also we're going to talk about the application afterwards. And I'll be focusing more on the basic, and because I think that once you understand the basic, the application is actually not that hard to know, to understand. So there'll also be a lot of proving right here for some theorems and all that, just to let you know. Yeah, and I guess we can just start with the basic. Okay, so what is a group theory? Basically, so we have learned about set, right? So what is a set? A set consists of elements. So let's say we have A, B, C, a lot of elements. So this we call a set. This is a set. But what is a group? If we introduce another operation, another binary operation, so this binary operation will take in two parameters, fx, x and y. And this parameter, this x, is an element from x, and y is an element from s. And from after using this binary operator, we will get back another element, maybe z. And this z must also be in s. So if we have a set right here, and we introduce a binary operation, then if this operation satisfies certain properties, we have a group. So basically, this is what the whole group is about. Yeah. Okay. For example, let's see the group of integer under addition. So we know that there's an integer set, which is, sorry, give me a moment to change my pen. Yeah, so we know that there's an integer set. Integer set consists of integers like 0, 1, 2, and all that stuff. And if we introduce another operation, so we call this operation the addition. The addition operation basically takes two integers and add it together. So if I have 0 and 1, I add it together, I get 1. If I have 1 and 2, I add it together, I get 3. And what are the properties that this addition satisfies? Adding two integers will always result in another integer. This is also known as the closure property. Basically, if you take any two element from the integer set, you add them, you always get back another integer in the set. And addition in Z is also associative, means that you can put the bracket in whatever in the expression in whatever order you want. So it's like A plus B plus C is equals to, so if you bracket here, it's also equals to if you bracket the thing behind. So this is the associative property. And there's also the identity element in the group. Identity element means that you can have this identity element, which is 0, and for any integer you add, you always get back the integer. So let's say if I have an integer A, I add this integer A to 0, I'll always get back the integer A. Yeah, so this is the identity element. And every integer also have a negative counterpart. A negative counterpart basically means that there's like some kind of inverse. So let's say an integer A again, and we have a negative counterpart minus A. If I add A and minus A together, I will get back the identity element 0. So this is the inverse property. And this is the identity property. With all these 4 properties, we can form a group. And now let's look at some other example, which is the group of rational number excluding 0 under multiplication. Multiplying 2 rational number will result in another rational number, as we all know, right? For example, yeah, if I have a rational number like A, B, if I multiply another number C, D, I will get A times C, B times D. And note that I'm using the multiplication operation here. And multiplication is also associative, and there's an identity element 1. So if you take 1 multiplied by any rational number, you always get back the initial number that you take. And every rational number other than 0 has an inverse. Because we can just, like for example, we have rational number A divides B, the inverse is basically just B divides A. So you just reverse the whole thing, and then you get back the identity element 1. Note that we must exclude the 0 element here. Why is it the case? Because 0 does not have an inverse. And in group, right, one of the axioms is that every element must have an inverse. So 0 cannot be in this group. So I just exclude this group from this from this set. And this is some basic example on how a group theory works. So before I move on to talking about the definitions and the axiom, now I just want to introduce some of the great application of group. Group is one of the algebraic structure in abstract algebra, and many applications of group theories and mathematicians have used them to solve a lot of hard problems. For example, we have the Fermat-Last theorem. Fermat-Last theorem, which says that A raised to the power of n plus B raised to the power of n equals to C raised to the power of n, where n is greater than 2, you cannot find a positive integer solution. So this is actually proved by using some elliptic curve, group theory stuff, some advanced stuff, and it's one of the greatest proof by using group theory. And there's also the Abel-Ruffini theorem, which says that a polynomial with degree larger than 5, you cannot find a solution in radical. So you know that we have the quadratic formula, which is if we have ax squared plus bx plus c equals 0, we know that x is also equals to this formula right here. Yeah, so people have been trying to find, is there explicit formula for degree 5 or above, but they have just proved using group theory that there's no such solution. Yes. So that's the application part. Yeah. Oh my God. Okay. Does anyone have any questions? I seriously feel like I'm talking to a wall. Hello.
No, all still good. All clear.
Yeah, okay, yeah. Then I'll just move on. Okay, definition and axiom. So just now I talked about some examples of groups. So now let's just talk about the axioms and the definition. A group is a set G together with a binary operation. And this binary operation, you can just let it with any symbol you want. Usually we just use, the addition and the multiplication. But for generality, I just use the diamond operation right here. And I'll just call this diamond because it's a diamond. And if you want to represent a group, you can use this bracket thing. And from right here, you write down the set, and right here, you write down the operation. Okay. And what are the 4 group axioms? First one is the closure property. For any 2 elements, A and B in G, once you apply the operation, you always get back an element in G. This is the closure property. And if you want some fancy mathematical notation, it's right here. And the second one, the associative property, which is like the bracket, you can put whatever order you want. And the identity property, which says that there exists a unique identity element E such that for all element A in E and G, A diamond E will be equals to A. And it's true also for another direction. So this identity element is like doing nothing. you just return back the other element. And last, we have the inverse property, which says that each element in A in G must exist a unique element A inverse, which we use this symbol to denote it, such that A diamond A inverse will be equal back to the identity element. Yes, and this is it. So these are the 4 group axioms that that a group must satisfy. And note that we do not need to have commutative property. Commutative property is the fact that A diamond B is equals to B diamond A. This property does not have to be satisfied in a group. And we have another name if the group satisfies this property, which we will see later on. So this is the abelian group. If the group is commutative, we can just call it an abelian group. An abelian group basically a group that satisfies one more axiom, which is the commutative property. Yep. We also have the finite group. Finite group are groups that have a finite amount of elements. Let's say just now we have the integer set. So integer set, you know that we have infinite amount of integer. This is an infinite group. This is an infinite group. But if we have a finite group, it means that the set has finite amount of elements. For example, the integer group under addition modulo n. So we use this notation to represent the integer group under addition modulo n. So let's say if I have a set that consists of maybe 0, 1, 2, 3, then this is Z for Z, right? There's actually more meaning about this notation. It's actually called a quotient group, but I'm not introducing the quotient group right here. So you can just think of it like just another bunch of set. Yeah, and this is the addition operation. And most of the group commonly used in cryptography are finite group because we don't really have infinite amount of resources and all that. So finite group is good because it's good. It's good. It's good. So let's get back to the initial example. I've just shown that I just given an example that this integer under addition is a abelian group. And this is the proof for it. Basically, the closure property, the associative property, the identity, the inverse and commutative, all of them are satisfied. And this is the integer property that we all know from our school. And it's also same for the rational number excluding 0. It's also same. Everything is same. You can just look back at the slide if you want to have more reference on it. So some quizzes. Which of the following are groups? Okay, what is this? So what this means is basically X is a matrix 4 times 4 that every entry is a real number. Okay, every entry is a real number. And the determinant of this X is not 0. And we are using the operation multiplication. So is this a group? Some responses. Maybe you can use the yes or no or something like that. So is this a group? Yeah. Okay. Yes, I see some responses. Yeah, this is indeed a group. Because and it's actually called a general linear group. It's also denoted by this symbol or this symbol, where n is the dimension of the matrix. There's also the special linear group where it's a general linear group, but with determinant 1. And this linear group, this general linear group is actually quite useful in some parts of cryptography. And one of my challenges actually based on this problem, this general linear group, but it just met a little bit of problem and I could not finish it on time. Yeah, so know this group, general linear group, is very interesting. And then the next one, complex number under addition. Under multiplication. Is this a group? Some responses. Yay. Yeah. So 3, 2, 1. No, this is not a group because 0 is in complex number and 0 does not have an inverse. So, however, if you exclude the 0 element, it is a valid group. Yeah. So this is kind of like a trick question. And last, we have this polynomial. So basically what this means is that the polynomial and it has a degree of 2 and the coefficient is the rational number, and it is from under addition. So is this a group? Yeah. 3, 2, 1. Sorry. Yes, this is also a group because if you can check, all the properties are satisfied, and this is, yeah, to prove that a set and operation forms a group, you just need to prove the 4 axioms that yeah. So now let's look at finite group. Finite groups are more popular and applicable in cryptography, and one example is the integer under addition modulo n. So like I said just now, if we have this integer modulo 3, then we can make out all the operations because we can basically combine everything, any like 0 plus 0 and 0 plus 1. We just try every combination, and we can see that if we use the operation, we can always get back the element back in the set, right? 1 is in the set, 2 is in the set, and so on. And because this is not really good to see, to have a better picture, we can use this table called the Cayley table. So the Cayley table basically is like the top row has the element, and the most left column also have the element. And this is like 1 plus 0 is equal to 1, 1 plus 2 is equal to 2, 1 plus 2 is equal to 3, and modulo 3 is 0. So this Cayley table is very useful because it gives us a better picture on how the group actually looks like. And we also have, the integer modulo 5, and this is the Cayley table. You can see that it's just kind of a cyclic structure. Like this 0 will move back to this side, and yeah, it's very beautiful, I think. And there's also the multiplicative finite group, which is the group of integer under multiplication modulo n. So from the examples that I gave just now is all under addition, but if we change it to multiplication, we also have another group. But in this group, n must be a prime number. Why is that the case? Because let's say if I have this group right here, and the operation defined in this group is basically fx times y equals to xy mod 4, right? Mod 4. And the problem is the 2 element does not have an inverse. This does not exist. This does not exist. The reason for this is because 2 and 4 have a GCD of 2. The GCD of 2 of 4 is not equals to 1. It's equals to 2. That's why it does not have an inverse. So if we want to have this multiplicative finite group and group of integer under modulo n, this n must be a prime number. Yeah. And some examples. So I can use this symbol to denote, or for easier reason, for simplicity, I can just use this symbol to denote the multiplicative group under modulo 3. So as usual, we can write down the Cayley table, and this is the Cayley table for integer modulo 5. Yeah, so 2 times 4 is equals to 2 times 2 is equals to 4, and 2 times 3 is equals to 6, and 6 modulo 5 is equals to 1, and so on. Okay, yeah. So before I go to this subgroup, because this subgroup is actually the biggest part of this lecture, I think. Subgroup, I have like several proofs for some theorems in this subgroup. So before I move on, any questions until here, just to make sure that everyone is on the right track. Yeah.
Nope.
Yeah, okay, then I guess I will just move on. Okay, subgroup. So what are subgroups? Sorry, give me a, let me take a look at the chat first. Okay. No, wait. Yes, what are subgroup? Let's say we have a group G, and H is a subset of G. If H also forms a group under the same operation as G, which I use diamond right here, then H is a subgroup of G. And we can use a notation less than or equal than right here. So direct implication from this is that we know that every group, every set, we must have the set itself as the subset, and we must also have the empty element, right, as the subset. And the trivial subgroup of any group is a subgroup that consists of just the identity element. And every group must have this trivial subgroup, right? Because every group must have an identity element. So you can always take the identity element out and it can form a group itself. We can also have another group, which is another term, which is called a proper subgroup. So a proper subgroup is a subgroup H, but it's a proper subset of G. That is, H is not equal to G. And this is usually represented notationally by H is less than G. So if H is not equal to G, and H is a subgroup of G, then H is a proper subgroup. Yeah. So if G only have two subgroups, which is the trivial subgroup and itself, then it's also called a simple group. Yeah, the simple group. So this is actually quite similar to prime number, which you have, like for every prime number you can have the itself, it can divide by itself, and it can also divide by the identity element 1. This is very similar to the concept of prime. So I think someone also called the simple group as prime group, but the most used name is called a simple group. Some examples. Let's say if I have this integer under a modulo 8 under addition, and we have these 4 subgroups. You can check by yourself that all of these form the subgroup. So the first one is the group itself, and the last one is the trivial subgroup. And let's look at this third one. 0 plus 4 is equals to 4. 4 plus 4 is equals to 8, and 8 modulo 8 is equals to 0. So this group itself form a group. So this is a proper subgroup, and it's the same for this. It's just yeah, the same thing. And if we have integer modulo 10, it's also quite similar. So you have the group itself as the first one, and you also have the trivial subgroup and 2 proper subgroup right here. And for this one, this is the integer modulo 7 under multiplication. This is a simple group. That's why you only see two subgroups available for this kind of group. Yeah. So some examples of subgroup. Subgroup is just subset, yeah, subset, but with some kind of fancy name, I think, guess. So next, let's talk about Coset. Coset is a little bit more, I guess you can call it complicated, right? So let's say H, I have a G group, and I have a H as a subgroup. So the left coset of H are the sets of this thing. This G. So if I take every element G from the subgroup from the set G, I can form a set G times H, G0 times H, and G1 times H, G2 times H, G3 times H, and so on. And what does this G0 times H means. This means that I just take the G0 and I multiply it with every element in H, and then I get another set. So what a coset basically means is that coset is a bunch of sets. So this is a set G0H. This is a set, okay? And we just call this a coset. And this is also a coset, and so on. I take every element G from the big group G, and I just multiply it with a subgroup H. This is a coset, a coset, a coset. And this bunch of whole thing, I call it a cosets, right? And left coset is when you multiply on the left side, and right coset is when you multiply on the right side. Yeah, and this is coset. So I'll give a little, I'll give more example later on, so you can have more clarity on what is going on.
Sorry, coset. Can we think of cosets as like just like power set, but for two different sets kind of thing?
Power set, yeah, like, but you mean by power set, you mean like, you know, the direct multiplication?
Yeah, as in like you just multiply two sets in a way. Like instead of with itself.
Yeah, but if you can think of it like this, you can think of it like this. But if power set, you basically have something like, let's say this is H0. So if I have this coset right here, so you have this element G0, H1, like this. But in coset, we can just multiply this together. So I guess it's similar. It's similar to power set, but you just take the element G and then you multiply with every element in H. Yeah. Yeah, I think you can interpret it as a power set.
Okay, see, thanks.
Okay. So some interesting property about coset is that coset of H are equal size and disjoint. Means that if an element, let's say if I have element G, an arbitrary element G, and I call this GK, this GK appears in some coset A, then this GK will not appear in other cosets such as B and C and all that. And I will prove this later on. And also left coset is identical with right coset and abelian group. Yeah, because the G multiply H is equal to H multiply G. Okay, some example of coset. Let's say if I have this subgroup H from here, what are the cosets? I can take 0 and I add it with this H subgroup. And this 0 plus 0 is equal to 0, 0 plus 2 is equal to 2, 0 plus 4 is equal to 4, and so on. And I can also add the element 1, because this element 1 is in the set G, right? This element 1 is in the set G. So 1 plus H equals to 1, 3, 5, and 7, so on. So you just basically take this element 1 and you just add it with every element in H. And note that we can also have 2 plus H, but 2 plus H is equals to 0 plus H, because 2 plus H is equals to 2, 4, 6, and 0. And you know that the order doesn't really matter in sets. So 2 plus H is the same thing as this. Yeah. And if we have this coset right here, we also have 0, 1, 2, 3. Yeah. So these are all the cosets of H. And integer modulo 9, if we let H to be this subgroup, the following cosets are below. 0 plus 0 equals to 0, 0 plus 3 equals to 3, 0 plus 6 equals to 6, and so on. Yeah, so these are the cosets. And note that, like, for example, you take 6, for example. If you found 6 in this coset, 6 will not be appearing right here. If you found 4 in this coset, 4 will not appear right here, anywhere else. It will only appear in one and only one coset. And every coset are the same size. The main reason for this is because you just multiply the element with H, and then you get another set. That's why all of these cosets must have the same size as H, right? Now this is very, I'll prove this later on. I see someone saying something in the chat. Order in set is not important. Order, Orders, I'll also talk about order later on. Okay. You mean the you mean the ordered set in in programming. Yeah, okay. But in mathematical meaning, I think order is You make a great point. Yeah, equivalent classes. I'll show that how Coset will partition the group H with a proof later on. And now let's just move on with another term, which is called the generating set. If S is a subset of a group G, then we can write this symbol as the subgroup generated by H. So what does we mean as the subgroup generated by H? The subgroup generated by H means the smallest subgroup of G containing every element of S. Let's say if I have a S with these two elements, 0 and 3, and the generating set of this is 0, 3, and 6, because this is the smallest subgroup that contains every element in S. We can call this a generating set of group. And we also have this kind of thing called a cyclic group. A cyclic group is a group that can be generated by a single element. Let's say we have this integer modulo 5 under multiplication. Why is this a cyclic group? Because 2 can be the generator. Let's say if I let S to be 2, this means that the generating set of S is actually equals to the group itself. We call this 2 the generator. I can make a simple proof for this. So let's say you have 2 to the power of 0, we have equals to 1, right? 2 to the power of 1 is equal to 2, to the power of 2 is equal to 4, to the power of 3 is equal to 8, and 8 modulo 3 is equal to 3. So we have 1, 2, 3, 4. And every element in this group can be generated from here. Yeah. And if we take integer, if you just take under addition, integer modulo and under addition, it's also a cyclic group because 1 can be in a generator. Let's say if I have a set 1 and I want to generate this group. To generate the set 1, to find the smallest subgroup that contains 1, first we must have the identity element in it and the set itself. And now 1 plus 1 is equal to 2. So we must also have 2 in it. 1 plus 2 is equal to 3. So we must also have 3 in it. And we will go on until we have n minus 1. Yeah. So all the integers modulo n under addition is a cyclic group because 1 can be the generator. And this is not the case for multiplication group. And to be honest, it's actually quite hard to find the generator in an arbitrary group. There does not exist such a easy algorithm to just find all the generators and all that. So if you can find a generator, then it means that it's a cyclic group. And there's also the thing called the group order. The group order is basically just the number of elements in group. So let's say if I have G is equals to 0, 1, 2, 3, the group order which we denote by this symbol is equals to 4 because there are 4 elements in it. And there's also the term called the order of element. The order of element, by simply saying, is just GK. When you do the multiplication operation on itself k times, it will equal back to the identity element, and the order of this element is equals to k. So k is this smallest positive integer such that when you multiply itself k times, it will get back the identity element. Yeah. Why is this called the order? Why this does not have any relation with this group order, right? If you see right here, but there's actually a really nice relation, right? And I will prove it later on. The order of group is infinite if there's no the order of element is infinite if there's no such k. So for example, we have mod 4, right? Okay, this is not a good example, but yeah, basically, let's say if I have the group of integers, the group of integers, and I take the element 2. So 2, if you raise it to any power, you know that it will never be equals back to 1. It will never be equals back to 1 because this is an infinite group and this number just get larger and larger and larger. But if you have, let's say, if you have z and z under modulo n, there might be some case that when you raise it to a power of k, it will be equal back to the identity element, which is equal, which is equals to 1. This should be right. So the order of every element of a finite group is finite. Means that if I have a finite group, so I like the finite group right here. I like the finite group. Every element in G, there must be some element, there must be an integer k such that it is equals back to the identity element. This is what this statement is saying. And the order of element also equals to the order of subgroup generated by the element. So let's say if I let a subgroup, let a set S and the subgroup G generated by this G, the order of this is equals to k. Yeah. Why is this the case? I'll show you later. Okay, some examples first. Integer modulo 5 under multiplication. You see that this is a finite group, and sure, it really exists an positive integer k such that for every element, when you raise it to some number k, it will be equal back to the identity element 1. I think this is a very special, very interesting thing to know. Okay, so now let's try to prove this. The order of every element of a finite group is finite. How can we prove this? How can we prove that if we have a group G, and I take an arbitrary element from G, and I raise it to any power, and I raise it to a power k, it will get back to an element, to the identity element. How can we prove this? How can we prove this? Some intuition. Okay, some intuition. So we know that G, if it takes to the power of 0, by definition, is equal back to the identity element, right? And if we take G, and this G might be equals back to the identity element or might not. We just assume G is not equals to the identity element. So now we have 2 items right here, and this is G takes to the power of 1. And when we raise G to a power of 2, this element can be equals to this or can be equals to this, right? And once I found an element, let's say I put here n minus 1. Once I found an element that is equal back to, let's say, this element, this, let's say equals back to this element, then Gn plus 1 is basically just G4. If Gn is equals to G3, right? So because we know that this is a finite group, and if this is a finite group, one of the element behind must be equal back to the element in front. And if we found such a cycle, if we found like Gn is equals to Gm, then Gn plus 1 is just Gn plus 1, and so on. And the cycle goes on. Okay, so I have this beautiful diagram right here. We have G0, which is equal back to the identity element, and G1, G2, and so on. And we let that this Gn minus 1, and then the next element, which is Gn, is equals to n. So Gn is equals to Gm. So if Gn is equals to Gm, then this cycle will continue right here. And if this is true, right, then we can never get back k is equals to G0. Because no matter how big your k is, you always stuck in this cycle. You always stuck in this cycle. You cannot get out from this cycle, right? But what are we going to show right here is that this Gm is actually equals to G0. If we have the cycle back to the first element, then we can basically prove that the order of this finite group is finite. So we can prove that there exists a positive integer k such that this is equals to the identity element. So what are we going to prove right now is we need to prove Gm is equals to G0. Because you know this cycle must exist. So how can we prove this? Let's start with this basic thing. So we let the set G0, G1, G2, and so on. And we let, since G is a finite group, S must also be a finite group, right? S must also be a finite group. And let N be the number of elements in S. So here we have N elements. And the last element, which is the Gn right here, is equals to Gm, where N is larger than M. And since we know that the inverse exists in group, we can just multiply the inverse on both sides, and we get this thing right here. Gn minus N is equal to G0, which is equal to identity element E. And since N is larger than M, N minus M is larger than 0. So this N minus M is a positive integer, and 0 is not the positive integer. So there must exist a positive integer K such that G raised to the power of K is equal to the identity element. And if we prove that this is true, we also prove that this is true. Okay? And the order of element is equal to the order of subgroup generated by the element. This basically means this, right? The order of element is equal to K, right? You see that this is actually a complete group. And how many elements are right here? There are N elements. And we know that if there are N elements, Gn is equals to G0. And this Gn is actually equals to K. So this is equals to N. So the order of element is actually equals to the order of subgroup generated by the element. Okay? Yeah. So this completes the proof. So we know that. So what can we come from here? What can we come from here? What can we know from here? We know that if we have a finite group, I take any element in G in this group, and I do the multiplication on itself several times, I will always get back to the identity element when I'm in the right someday, sometime. Yeah. So this is a proof for this theorem. This is actually not a theorem. Yeah. So can anyone understand this? Or do you have any questions on this? This is my favorite slide of the lecture, by the way. No question? No question? Okay. Then I'll just move on. Okay. Yeah. Okay. I'll just make a quick pause right here before I go into another theorem, which is the Lagrange theorem. This is also it takes quite a little bit of time. You can see the proof right here. Yeah, this is the proof later on. Yeah, so I'll take a short break right here. Maybe I'll continue at 4 p.m. I hope you enjoy the proof just now.
Very, very enjoyable, but my brain a bit
It's like something you never think of, and then when you explain it, it kind of makes sense, but it's like you never really think of it.
Yeah, that's why group theory is very beautiful. But it's actually quite sad because I don't really have the time to talk about elliptic curve, and the slide for elliptic curve is just like it's not even introduction. It's just the telling you that there exists a thing called elliptic curve. Yeah, because I don't really have the time for it.
Future L2L, future L2L.
For part 2.
Yeah.
For part 2, we watch this whole thing again. Ooh.
Maybe you can do elliptic curve. Okay, I will continue on this on my slides right now. So Lagrange theorem, what is Lagrange theorem? If I have a group G and the order of group is this, and if I have a subgroup H and the order of subgroup is this, now Lagrange theorem says that for every subgroup, the order of the subgroup must divide the order of the group G. Yeah, this is Lagrange theorem. So what can we get from this Lagrange theorem? We just know that for any finite group G, and n is the order of group, let n be the order of group. So let the n be the order of group, and let k be the order of element. K be the order of element. We just know that G, when you raise to the power of k, is equals to the identity element. And since that Lagrange theorem is true, this k can divide, because this k is basically just the order of subgroup, right? This k is also the order of subgroup. And since that Lagrange theorem is true, this k can divide n, and there exists another integer k, a, such that a times k is equals to n. And I can raise this to a, and then I get g raised to the power of a times k. And a times k is basically just n. So g raised to the power of n is equals to e. This means that if my group has an order of n, okay, if my group has an order of n, I take any arbitrary element from here. G raised to the power of n must always be equals back to the identity element. Right? Must always be equal. No matter what element you take. If the order of group is n, you take any element, you raise it to the power of n, it will always be equals back to the identity element. This is also Fermat-Little theorem. So you know that in the Fermat-Little theorem, we have when an integer raised to the power of p minus 1, it will be equals back to 1. And what is this group? This is actually the ZPZ under multiplication group. And we know that this group excluded is just the integer under p excluded the 0 element. So what's the order of this group? The order of this group is p minus 1. So every element raised to p minus 1 will be equals back to the element 1. So this is Fermat's Little theorem. And if n is not a prime number, then if n is not equals to is not a prime number, then the order of this multiplication group is actually equals to the Euler's total function. And this Euler's total function is the number of positive integer up to a given integer n that are relatively prime to n. Basically, what this means is that if my n is 10, so I have then the Euler total function of 10 is 1, 3, 5, sorry, 6, no, 6, 7, 9, yeah, these 4 elements, right? Yeah, Yeah, these four.
So the total function includes 1.
Wait, actually, no, actually I'm not quite sure about this, but I think it includes. Yeah, I think it includes. Because no, sorry. Wait, does it include?
I legit don't know. I just asking.
No, I'm not too sure, but what I'm sure is that this Euler total function is equals to the order of this group. Yeah, it's equals to the order of this group. I'm not sure about the total function includes 1 or not, but yeah, I think it includes 1 because relatively prime basically means that the GCD is equals to 1.
Well, makes sense.
Yeah, the GCD is equals to 1, so I think it includes 1.
Okay.
So yeah, so if we have this Lagrange theorem, we can easily prove Fermat's-Little theorem and Euler's theorem. But the problem is, how can we prove this Lagrange theorem? So here's the proof. Okay, let G be an element G, H be a subgroup with a binary operation. Yeah, so this is basically just introduction. Okay, prove that G must be one of the coset of H. Remember about the coset. Now we prove Lagrange theorem using coset. Why do we prove Lagrange theorem using coset? Because we know that the cosets of H. Okay, so we know that the cosets of H consists of what? Consists of G0H, right? G1H, G2H, and so on. And we know that every of these have the same size. Every of these has the same size. If this G, every element of G can only be in one of these coset, that means that this coset of H will partition the group G into, sorry, click wrong. Yeah, we partition the group G into a bunch of cosets. And if we can partition the group G into part of coset, since we know that all of this is the same size, and let's say the size of this is K times the number of coset will be equals to the group size. And this K is actually the size of H. So we are using coset to prove Lagrange theorem. So if this is true, right, Lagrange theorem is true because you can just divide it, right? So how can we prove that G can only be in one and only one coset? G must be in one of the coset. We prove by existence. So this is existence. We prove by existence first. We prove the existence. Since H contains the identity element, we know that this coset must exist in one of the coset, and G multiplied by H, which also contains the coset itself. So this is so G must be in one of the coset. And prove that every coset that contains G are the same. How can we prove this? So first we let two coset that contains G. If we have coset A and coset B that contains G, and this G1 and G2 are different. Okay, this G1 and G2 are different. That's why these two are the, yeah. So now what we want to prove is that we want to prove that A is equals to B. If we can prove that A is equals to B, then we can prove that this G must only contain in one coset. Okay, how can we prove this? Let H2 be two elements from H. And since we know that G contains in A, we know that G contains in A and G contains in B. It means that there must be some element H1 and H2 such that G1 multiply H1 is equals to G. That's because if this is not true, then G is not contained in A. So there must be an element H1. When you multiply this is contained in A. So G1 times H1 is equal to G2 times H2 is equal to G. And when we have this, we can just move H1 to the other side, right? H1 to the other side. And we multiply H on both sides again. And what is this? Okay, G1 times H. What is this? This is basically an element in A, right? And what is this? This is H2 times H1 inverse times H. This is an element in H. This is G2. So G2 times an element in H means that this whole thing must be an element in B. So what we have just proved? We have just proved A is a subset of B. Yes. And similarly for the other direction, B must also be a subset of A. Therefore, A is equals to B. Okay. And from that, we just proved that the coset of H partition G into disjoint set of equal size. So the order of coset divides the order of G. And since the order of H is equal to the order of coset, Lagrange theorem is true. And this completes the proof for Lagrange theorem. Okay, any questions? No questions? Then I just move on. Why isn't this fine, my favorite? Because I don't have any diagram for this slide. I think the previous slide is better because of the diagram. You know, drawing using latex is very interesting.
Hey, can you go back and recap what is Lagrange theorem?
Oh, Lagrange theorem basically says if I have a order, if I have a subgroup H and the subgroup of this must divide the subgroup of G. So if H is a subgroup of G, then means that G, the order of G must divide the subgroup of H. Sorry, order of H must divide the subgroup of G.
Yeah, then how do we link it to proof?
Because we can prove it using coset. The coset of H contains of bunch of element, bunch of G1H, G2, and so on. And we know that all of these are the same size. All of these are same size. And since all of these are same size, if you can prove that for every element G in the big group G, this G can only be in one of the coset. It cannot be in more than one of the coset. Then it means that the total order of the order of the group G is equals to the order of G0H times the number of coset. And this G0H is basically this. These two are the same.
Kel Zin, I have a question.
Yeah.
Let's say we have a H that partitions G into 4 disjoint sets.
Yes.
Is H unique?
You mean is subgroup unique, is it?
Is it possible to partition G into 4 disjoint sets? Multiple different ways in which we can partition G into 4 disjoint sets?
If you okay, okay, I know what you mean, but yeah, I know what you mean right now. Basically, I think what we are supposed to, if you want to partition G into different sets, right, you must have the H subgroup first. Right, you must have the H subgroup first. If you want to exactly partition a group G into 4 sets, into 4 cosets, that means that the subgroup of the subgroup that you use to partition must be the order of G divided by 4. If you can find such a subgroup, then you can partition G into 4 cosets. Yeah, does that answer the question? Yeah, so if you want to partition G into some arbitrary number of cosets, you just need to find the corresponding subgroup first. If you found a subgroup, then you can partition it. Yeah, this is actually quite similar to the modulo thing. Yeah, just ignore what I said.
So is it the case that for any size subgroup that I want to find, there will always only exist a unique subgroup of that size?
Unique sub. I'm not too sure about that, but I guess there can be a case where you have 2 subgroups with the same size, but they are different. Yeah, I think that case might be possible. You might have two H1 and H2. So this H1 and H2, although they have the same size, but they might be different. I think that that might be possible, but I'm not too sure about it. But yeah, you might have the case that they are different.
Okay, thanks.
Yeah. Any more questions? Okay, then I can just move on. Next part, homomorphism. Okay, homomorphism. I'll just, before I write down the definition, I just write down the gist of it. So let's say if I have a group G, and I have another group H, and this G and this H, I want to find a mapping such that for each element G, I can convert into an element H. And the group, all the group operations still maintain after the conversion. So this is what we call the homomorphism. Basically, we have two groups, G and H. A group homomorphism is a function that F A diamond B is equals to FA times FB. Note that what is this? A diamond B, this is an element from G. What is this? This is an element from H. This is an element from H. And this is an H operation. And this whole thing will become a H. So basically, you want a function that even though you can make the operation first or not, it doesn't matter. You can just do it separately under the group H, or you can just do it on group G first, and then you just convert into some element in group H. Yeah, so this is group homomorphism. And some properties about homomorphism is that it maps the identity to identity. So EG, F of EG will maps to identity of group element G, will maps to identity of group element H. And it also maps the inverses to inverses. Okay, note that this is an element in G, and this is an element in H. And once this is an element in H, this is an element in G. So basically, it means that the order doesn't really matter. Okay, if this function is injective, then we call it a monomorphism. If this function is surjective, we call it epimorphism. If it's bijective, isomorphism. If it has the same domain and codomain, then it's an endomorphism. If it's an endomorphism and bijective, then it's an automorphism. Yeah, so these are the types of homomorphism that that exist. So I'll give some examples later on. Like, yeah, here. So let's say if I want to map, if I have a group, so this is a group, right? This is a group, and this is another group. This group G is Z, and this group H is Z, 5Z. I want to map this to this. How can I do the mapping? So I let the function F. This function takes an element from G. So this function is from G to H. Okay. So this function takes an element from G. And how do I map a Z from here to a Z from H? I just do modulo operation. Right. And now I want to prove that the group homomorphism is true. How can I prove this? I let two elements Fx plus y. So this is an element in G, okay? And by our function definition, what is this? This is x plus y mod 5. And x plus y mod 5 is basically equals to x mod 5 plus y mod 5. And what is x mod 5? What is y mod 5? This is fx. This is fy. So you just prove that fx plus y is equal to fx plus fy. And note that this is actually, oh, sorry, you need another mod here, to be honest. Yeah, you need another mod here. And this is the group operation in H, but this is a group operation in G. Yeah, So by this we prove that this is a group epimorphism. What is epimorphism? Epimorphism is surjective. So F is surjective. Okay. And another example, which is this. How can we prove? How can we map something from, the integer under modulo 2 to the integer under modulo 3 under modulo 3 under multiplication? To do this, we can just write down the Cayley table. We can see that the Cayley table for integer modulo 2 is this, and the Cayley table for integer modulo 3 under multiplication is this, and just map the element one by one and just see that it's actually just x plus 1, right? So this is a group isomorphism. Yeah, you can just change this 1 to 0, change it 1 to 0, 1 to 0, 2 to 1, 2 to 1, 2 to 1, 2 to 1, and this is 0, and this will become the same thing. This is group isomorphism. Yeah, any questions? Yeah. Okay, no, then I'll just go on. Okay, some properties of homomorphism. By homomorphism, you can transfer a group from one to other. Sometimes a problem is easier to solve in other group. So this is very useful. Let's say if I have a group G, and I want to solve some problem in group G, and this G is very hard to solve a problem in group G. But we know that there exists an isomorphism to group H, and we know how to solve the problem in group H. So what I can do is I map the thing to H first, and I solve the thing in H, and then I just map it back to G. So I just solve the problem in G. So this is, like the problem reduction in NP problems, NP complete problem. Yeah. And all the groups that have prime order are isomorphic with the additive group under addition. Note, this is all the groups, right? All the groups. No matter what group you have, okay, no matter what group you have, if you have a prime order, then it is isomorphic to the additive group modulo P. This is true. This is always true, right? And all the groups that has order less than 3 are isomorphic with each other. So if I have a group that has an order of 3, and I have another group that has order of 3, without knowing anything, I know that these two groups are isomorphic with each other. Okay, but I will not prove this, but this is actually not too hard to prove also, but yeah, you can check the proof online. Every infinite cyclic group is isomorphic to the additive group of that, and every finite cyclic group of order n is isomorphic to the additive group of this. Yes, so yep, that's some interesting property about group homomorphism. And there's also a thing called a kernel group, and this is actually not quite important, but it's just that the kernel group is the set of elements of G which maps to the identity element in H. So it's basically a bunch of element that maps to the identity element. Yeah, so this is the kernel group.
I have a question.
Yep.
Just now you said that part where you show the all the groups that has order less than 3. You showed that the order of G equals to 3, and that's not less than 3. That's equal to 3. Is it less than or equal? Oh, okay.
Sorry. Less than or equal to, yeah.
Okay. Thanks.
Yeah, I guess I can just make out why is this true? Why is this true? Because this is, I think this is also quite interesting. So if I have an order, okay, let's say I just take I need some space. Okay, I'll just use here. Okay, so why does everything that has why can we know that? Why can we know that if I have a group of order 3 and I have a H another group of order 3, I can always show that these two groups are isomorphic with each other? The reason is that if we can draw the Cayley table out, okay, if you draw the Cayley table out, we have 3 items, right? We have 3 items, and this operation can be anything. Okay, yeah, this operation can be anything. So we know that the first element must be the identity element. So we just put E here. And this is A and B, okay? any arbitrary element. Okay, E and E must be E. E and A must be A. E and B must be B. Same for this too, right? Okay, what is A and A? Okay, can it be A? No, right? Why it cannot be A? Because if A and A is A, if A and A is A, but A and E is also equals to A, then it means that A is equals to E, which is not true. So this must not be A. And what do we have left? We have E or B. So A and A, can we be equals to E? Let's try to put it here. Okay, let's try if this is equal to B. If this is equals to E, this must what left with this is B. But this cannot be B for the very same reason. Basically, you cannot have the same row or same column to be the same element. So it's like solving Sudoku. We know that this must be B, and this must be A, and this two must be E. So by construction, this is the only possible group with order 3. It must be such it must be in such property. Yeah. Like if I take 0, 1, 2 for some example, plus 0, 1, 2, 0 plus 0, 1, 1, 2, 1, 2, and 1 plus 1, 2 modulo be equals to wait. This is modulo 3. Yeah, this is 2, and this is 1, and this is 0. This is 0. Yeah, 1 plus 1 is equal to 2. 1 plus 2 is equal to 3. 3 modulo 3 is 0, and yeah. So no matter what, you can only form this kind of group because it's based on construction. So this is the interesting property of group isomorphism. Okay, group R. Okay, so now let's talk about ring. So what are rings? Rings. Okay, rings. So we have introduced what is a group. We know that group are set of elements with one operation. But now what if we have two operations? If we have two operations and it satisfies certain property, then we call it a ring. Right? Yeah, the definition. A ring is a set R with two binary operations, addition and multiplication. These two symbol can be anything. It can be diamond. It can be some you know, some E or something. Yeah. But we just for easier to understand and for simplicity, we just use addition and multiplication symbol. And 0, we denote 0 as the additive identity and 1 as the multiplicative identity. And first, R must be an abelian group under addition. So if we take out the multiplication, the ring R is an abelian group under addition. Okay, and multiplication must be associative. Multiplicative identity must exist, and multiplication and addition is related by distributivity. So distributivity is basically the same thing that we learn from school, and it's true for the left side and the right side. This you note that we don't really need to have inverse, multiplicative inverse. We don't really need this to be a ring. You don't need to have multiplicative inverse to be a ring. You just need these three, which is associative, identity, and distributivity. And it's also an abelian group under addition. So this is what a ring is. If a ring is commutative, means that if the multiplication operation is commutative, then it is a commutative ring. And it's a unit if an element has a multiplicative inverse. An element is called a unit of a ring when it has a multiplicative inverse. The set of unit of the ring form a group under multiplication. And this is denoted by the symbol this. Note that we have used this symbol quite a lot of times. This is basically the group of units. So because the sets of units form a ring of group under multiplication, because everything has if we form a group using unit, that means that every element has a multiplicative inverse. So it forms a group. Some examples of ring. So this is the integer ring, and this is the integer modulo n ring. This is the polynomial ring. Sorry, this symbol we use basically means that we want a polynomial, and then the coefficient is this front guy. So let's say we have ax squared plus bx plus c. This a must be z, must be an element in z. B must be an element in z. C must be an element in z. Yeah, same thing for this symbol right here. So if we use this symbol, means that every coefficient must be an element from that ring. Yeah. And this is also a ring. This is also a ring. Real number is a ring. So that's all about ring. Some properties. Additive identity 0. Multiply any other element. Sorry. The notation doesn't say the degree of the polynomial. Yeah. I forgot if we want to say about the degree or what are the notation that we use, but I just know that if we want to represent a polynomial, you just use that bracket symbol. I think there's another specific notation if we want to represent the polynomial with degree. Maybe we just write the n somewhere here or somewhere here or some, yeah. But I think yeah, you can maybe find the notation online. Okay. Additive identity. Multiply any other element equals back to the additive identity. So now we need to prove this. If we have an additive identity 0, we multiply any other element in G, we always get back the additive identity. Why is this the case? Why is this the case? We want to prove this. So how can I prove this? To show off my proof, I'll just prove it on the spot. Okay. We know that multiplication and addition is related by distributivity. So what can we say about this is that basically what we want to do is we want to add 0 G times. And we know that if we add 0 G times, we always get back the thing 0. So this computes the proof that additive identity multiply any other elements equals to the additive identity 0. Okay, yeah, that's the proof. And additive identity does not have a multiplicative inverse. So if I have an additive identity E, I want to prove that this does not exist. This does not exist. How can I prove this? So we just prove that E multiply any other element will be equals back to E. This is additive. But multiplicative inverse is if EA multiplies EA inverse equals to the EM. EM is the multiplicative identity, which is also denoted by 1. So I want to find EA times EA inverse equals to 1. But we just proved that EA multiplied by any stuff will be always equals back to EA. So this must not be true. So additive identity does not have multiplicative inverse because additive identity multiply anything will be always equal back to the additive identity, and it will not be equals to the multiplicative identity. But what if additive identity is equal to the multiplicative identity? If additive identity is same as the multiplicative identity, then the ring only has one identity element. Okay, this is very trivial to prove. Like, let's say the identity is E. Since we know that, how can we prove that the ring only consists of one element? Suppose that exists another element A in the ring. this A multiplied by this additive identity, based on the previous proof that we have just shown just now, will always be equals back to E. But because it's also the multiplicative identity, it will also equals back to A. So E will also be equals to A. So if additive identity is same as multiplicative identity, then it only consists of one element. Okay, some interesting property about ring. Any questions before I move on? No? Okay. Yeah. Zero divisor. Zero divisor, by simply saying, is two elements, A and B. When you multiply together, you get the zero element. How this, if A and B is not zero, this is not zero, this is not zero, and this is not zero, then A and B is the zero divisor. For example, we have this integer modulo 6. We know that 2 times 3 is equal to 6, but when 6 modulo 6, it will be equals to the 0. So 2 and 3 are the zero divisors of this group. Similarly for integer modulo 10. If the ring does not have a zero divisor, it's called a domain. If a domain is commutative, it's called integral domain. Note that this zero divisor is actually very useful. If we don't have this zero divisor, we will have a lot of problems solving algebraic questions. We know that, like for example, we have x minus 1, x minus 2 equals to 0, right? And then we know that x minus 1 must be equal to 0, or x minus 2 must be equal to 0, right? And x is equal to 1, or x is equal to 2. Yeah, this is why can we have this kind of conclusion that only these two roots exist? The reason for this is because we know that in the ring R, there is no zero divisor. If there is zero divisor, let's say if this is modulo 6, then this can be 2, this can be 6, 3. So we will have another case where x is minus 1 equals to 2 and x minus 2 equals to 3. Yeah. So without zero divisor, it is very useful to solve this kind of problem. But a ring might have zero divisor, which is unfortunate. Yeah. So that's the thing about ring. And after talking so much about ring, now we can move on to the field. Field. Okay, I just take a 1 minute break there now first before I move on. Any questions for groups and ring? Yeah. These are all mathematics, abstract algebra. There is zero relationship with cryptography for now.
Oh, very good.
But if you want to solve, I think if like some very advanced crypto question, you know, those kind of roll your own crypto stuff, usually they just use some kind of group theory and ring theory to solve to create a new cryptography scheme. And yeah, but most of the crypto scheme that we use right now, we don't really need to have such deep understanding of group theories to solve them. Yeah. Okay, let's move on to field. Okay, field. What is a field? Field is basically just a ring, but with additional property. Field is a set F with two operations, addition and multiplication, and satisfy the axiom. What are the axioms? Closure in addition and multiplication, associative in addition and multiplication, commutative in addition and multiplication. Exists both identity. Every element has additive inverse. Every element other than the additive identity have multiplicative inverse. and distributive of multiplication over addition. So this is a field. You can also view field as ring with multiplicative inverse and no zero divisor. Also, another interpretation is that field are combinations of group with relation to distributivity. So if I have a group, if I have a group G, and under we know that this group forms a group under addition, and we also have another group which is formed under multiplication. If I have to combine this group together, then we get a field. Yeah. So field is just you just basically have everything in it. Yeah. You have multiplicative identity, you have additive inverse, you have multiplicative inverse, you have everything. So if you have everything, then you are a field. Some properties of field. Every field must have order of prime power, where P is a prime power. Yeah, you just call it a prime power. And the characteristic of a field is called the P, which is the power lah. Yeah. And all the fields with the same order are isomorphic with each other. So if I have two fields, and we know that this field have the same order, we know then these two fields must be isomorphic. This is also theorem. And we deny a finite field of order Q with this symbol. This basically means the the Galois field, or the GF means Galois field, and yeah, of order Q. Example of fields. If we take the integer modulo 5, then we have this field right here. This is the Cayley table. You can look at it. I will not explain too much about it. Cayley table is just group force. Yeah, basically group. Yes, group is addition and subtraction. Ring is yeah. Your interpretation is correct. Okay. Okay. Now, I'm going to prove this fact. Why is every field must have order of prime power? Why is this the case? Why? But I'm not going to prove this. But I'm just going to prove this. Why every field must have order of prime power? First, we need to know the Cauchy theorem. What is the Cauchy theorem? Cauchy theorem says that if G is a finite group and P is a prime, then P, if P divides the order of G, then G must have an element of order P. So if the order of G is P1, some power, maybe R1, P2, R2, Pn, Rn, then there must exist an element in G such that G has an order of P1 and G, yeah, and so and there might also be another element G1 that is P2 and so on. Yeah, and so on. So this is Cauchy's theorem. Why is this? Let's just prove it. Okay, take a non-identity element A from G and generate the subgroup H. Since that we know that P divides G, P must either divides H or G divides G, I forget the name for this, but yeah, you just know that it's this thing. Why is this the case? Because we know that from Cauchy's theorem, for Lagrange theorem, we know that H is H can divide G, right? So if G is equals to some P1 something, then this P1 might be in H. Okay, this P1 might be in H. So P must either divide H or divide the quotient of this thing. So let's look at the first case. If P divides the order of H, what can we do? Okay, we can construct another element K. So this K, we raise it to the power of order H divided by P. We raise it, we construct an element. And by this construction, we know that K has an order of P. Why is this the case? Because we can just move this P over here. and k takes to the power of p is equals to a takes to the power of order of h. And since that a is a subgroup generated from h, from the theorem that we proved just now, we know that this is the identity element. And because this is the identity element, this by construction, this k has an order of p. So if p divides h, then we just prove that we can construct an element k, and this k has an order of p. Yeah. So this is some kind of proof of construction. But for another case, I just skip the proof, but it's very similar. You just know that, and Cauchy's theorem is true. Okay. Any questions for this? Yeah, it's called the index. It's called the index. Okay, then I just move on. Order of finite field. So now we are going to prove why must every field must have order of prime power. Okay, let A be two non-identity element from the field, and let H be a group homomorphism. No, we just let a function first, and then we prove that this is a group homomorphism, such that Hx is equals to B times A inverse times X. Okay, so we just let the function first. And now we want to prove the homomorphism. HA plus A is equals to B times A inverse times A plus A. And since that this A times A inverse times A is equals to 1 and this is equals to 1, we can just, by the distributivity, A plus A is equals to B plus B. So we just prove that H is an automorphism. So automorphism, recall that automorphism means that the codomain and the domain are same. And this is a bijective function. And since that they are automorphic with each other, so they have the same order. By Cauchy theorem, if G does not have an element of order P, then G does not divide the order of G. But because every element of G has the same order, so every element must be a prime. The order of every element must be a prime, and the order of G must be a prime power. Yeah, so this completes the proof of this. Yeah, any questions? By the way, this is the you know the contra positive version of Cauchy's theorem. Cauchy's theorem initially says that if P divides G, if P divides G, Cauchy theorem, if P divides G, that means that there must be an element that the order is equal to P. So I just inverse it, and if P does not have an element of order P, then P does not divide the order of G. And because that every element G1, G2, G3, and so on, they all have the same order. They all have the same order because they are all isomorphic with each other. They all have the same order. And due to this fact, they all have the same order, we know that the order of the group must be a prime power. It cannot have another prime. Because if this is another prime, it will contradict the fact that everything, based on the Cauchy theorem. Yeah, so can everyone understand this? So I think this is my last proof. I have 4 proofs so far. Yeah, there's only 4 proofs in this slide. This is my last proof. No problem, then I just move on. Okay, so prime field. If we have a field with prime order, then it's called a prime field. If we have a field with prime power order where m is larger than 1, then it's called an extension field. But the problem is, how can we construct a field with a prime power order? Is this a field? But this is not a field. Because if, let's say, I have just proved just now that this 2 does not have an inverse. If we take P to be 2 and M to be 2, this is not a field because one of the element does not have inverse. That's why we cannot just build a prime field, build an extension field just like that. We cannot build an extension field just like that. But how can we construct a field with order of P takes to the power of M? The easiest way is to use the polynomial. So since we need P times P times P times C element, so there's M times right here. The simplest way is just use a polynomial. So if I have a polynomial and the highest degree is M-1, and for every element right here, the element is an integer modulo P. So or you can just write Z P Z. So, but you can use polynomial to solve the problem, the issues of cannot construct a prime power field using just integer. So you just use a polynomial to solve the problem. Yeah. So this is why usually when we denote sometimes like P to the power of A, it will be something. It will be some polynomials because of this. But there's also some issues with polynomial because if we use polynomial, we cannot use number arithmetic anymore. We must use polynomial arithmetics. And what are those polynomial arithmetics? So first one, we have the addition. If we have 2 polynomials, how can we add them together? Very easy. We just add every coefficients together modulo P. Every coefficients together modulo P. So for this x, you just add the coefficients together modulo P, x the coefficient together modulo P. But similarly, for subtraction, you just do the subtraction for every coefficient. And about multiplication, it's a little bit trickier. How can we do multiplication? Because if we have let's say if this one have a degree of m, this polynomial have a degree of m, and this h has a degree of m. And once I multiply these 2 polynomials together, GH, I get a polynomial with degree of 2m. But the problem is this 2m is not in the field anymore. It's not in the field anymore. It's not in the field anymore. So how can we fix this problem? How can we make sure that it is back into the field? The way to solve this is that we use a modulo operation, but now instead of modulo number, we modulo a polynomial. And this polynomial, we call it an irreducible polynomial. And by using this, we can also find the inverse. So the inverse is also can be found by using the irreducible polynomial. And what is irreducible polynomial? P is an irreducible polynomial in this field if P has a degree of m and there are no 2 non-constant polynomial AB such that A times B is equal to P. For example, is this irreducible polynomial? So let's see what contains in GF2. What contains in GF2? GF2 is basically equals to Z PZ, right? So it's equals to Z2Z. So we have what element? We have 0 and 1. If we multiply 1 and 1 together, we get 1. If we multiply 1 and 0 together, we get 0. We can never get x, right? So x is an irreducible polynomial. And what about this? Is this an irreducible polynomial? Let's just analyze what are the elements in this field. So GF4, 2 to the power of 2. Okay, GF4. We have what? We have 0. We have 1, and we also have x, right? And we have x plus 1 because this is the power of 2, and the highest degree is this minus 1. Yeah. So can we construct something that when these 2 multiply together, we get this? Let's try. X times x plus 1. What we get? We get x squared plus x. And x plus 1 multiplied by itself, we get what? We get x plus x squared plus 2x plus x plus 1. Yeah, so we can never get this. So this is an irreducible polynomial. But what about this? Is this also an irreducible polynomial? Okay, let's see. So just now we have just list out, right? We have just list out. And one of the element, if you recall, is x plus 1 and x. If we multiply x plus 1 by itself, right, we get x squared plus 2x plus 1. And since that we are doing in GF 2 to the power of 2, the characteristic of this field is 2. So we have to modulo every coefficient by 2. And if we modulo this coefficient by 2, we basically what we get is this. Because 2 will just get erased after the modulo operation. This is why this is not an irreducible polynomial. Yep. So that's the thing about irreducible polynomial. And if you want to, okay, if I have for every field, right? For every field, I can have multiple irreducible polynomials, and you can just pick whatever one you want, whatever polynomial you wish to use. It doesn't make a difference because of the isomorphic reason. If you have the same order, you will always isomorphic with each other. And this is one of the example of this, the Cayley table. If I take the irreducible polynomial 1 plus x squared, and these are the elements. These are the elements in GF2, 2 to the power of 2, and you just multiply together. This is just addition. This is a multiplication, and after multiplication, you just modulo this polynomial. And once you modulo this polynomial, every coefficient you also modulo the prime, and this is what you get. And also because this is because one good thing about polynomial is that you can represent it as bases. And when we have GF of 2 to the power of n, we can represent it in binary. So we just take the first x, right? If we have, let's say we have x plus 1, then we just take it as 3, because I just take it as the first bit. Sorry, the second bit, and this is the first bit. So we just take the degree, and if we convert everything into number, then we get this, which is nicer to look instead of all the polynomials. And this is the Cayley table for this one. Gaussian field. Sorry, not Gaussian, Galois field. Okay, and that brings us to the end of the basics. Any questions?
Sorry, can you go back to the slide with the irreducible polynomial?
Yeah, okay.
Yeah, this part, the definition of irreducible polynomial, the last P should be capital P, right? It means the polynomial.
Yeah.
Oh, okay.
Sorry for the
and also, is there like a very efficient way to find irreducible polynomial, or do we just have to guess and check?
I think there are some algorithms out there, but the easiest one that I have known so far is using SIF. So is using SIF. So let's say if I want to find polynomial of this 2 to the power of 2, right? And I have what? I know that 2 to the power of 2 have this element, have 0, 1, and 2, 1, x plus 1, x and x plus 1. X plus 1. So what I can do is I just use 0 and I multiply with 1 and multiply with 0, x multiply with this, and this I multiply with this, I multiply with this, and this I multiply with this, and then I just check. After all this multiplication, then I will certainly left out some polynomials that I didn't found yet, and that will be an irreducible polynomial. You can just, because you can represent this as number basis, so you can do some kind of SIF, like SIF of erratosis or something like that. So you just like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 or something like that. So let's say if I have 1 multiplied by x, so this is that. You can just cancel out and just use the usual method that you use to find prime numbers. But I think there's a more efficient way to find irreducible polynomial. But I just don't know what the algorithms is. But and certainly there exists lah. Yeah. Okay. Any more questions? Usually in crypto, you just copy.
Copy Sage code.
Yeah, copy Sage. And Sage will auto find the irreducible polynomial for us. But yeah. Okay. Now application discrete logarithm problem. Okay, since I don't really have much time left, I'll just run through it really quickly for this part. Discrete logarithm problem. What are discrete logarithm problem? Okay, if I have a group G, okay, if I have a group G, and I do a operation on itself k times. If I do an operation on itself k times, and I return you the element, the resulting element, which I call B, it's very hard for me to find K given G and B. It's very hard for me to find K given G and B. So this is the discrete logarithm problem. So for example, if I have a group of integer modulus 13 under multiplication, find K where 5 is, and this is one of the solution, and it's really not easy to find. But in additive group, it's very special. If we want to find K such that where K is equals to K times 2, note that this is actually very similar to this. The difference between the first example and the second example is the difference in operation. The first example, we use multiplication. The second example, we use addition. And for addition, we can use this kind of multiplication symbol. For multiplication, we use the exponent symbol. And to find this, it's not hard because we can just find the inverse of 2. If we can find the inverse of, inverse of 2? What? Yeah, inverse of 2. Yeah, inverse of 2. We can find the inverse of 2 and we multiply the inverse of 2 on both sides. Then we get K is equal to 5 times the inverse of 2. And inverse of 2 is equal to 3. And we get that K is equal to 9. And this is very easy to calculate, but not for this. So from here, what can we know that is that sometimes discrete logarithm problems is easy to compute, and sometimes it is hard. Generally, it is hard, but it is easy to compute in some special groups, such as the additive group modulo n. But what are we interested in? I'll talk about it later on. Okay, so why are discrete logarithm problem good? Because it's a good one-way function. You can easily compute the G takes to the power of K because you can use the double and M method, which you can compute the power in log K time. But if you want to compute the inverse, it takes a higher time complexity. And for example, the baby step giant step algorithm takes square root m times to compute the discrete logarithm problem. So if this K is something like 2 to the power of this will just take this much step, and this will take like this much steps. So it's very easy it's a good one-way function because it's easy to compute one way and it's hard to compute another. And it's also applicable to many groups. Discrete logarithm is hard to compute. So you can take any group, and if you found that the group is hard to compute, the discrete logarithm problem is hard in the group, then you can just invent a new cryptography scheme based on this discrete logarithm problem. Basically, this is also what I did in one of my challenge. I just invent another group, and then I just use I just want you to solve the discrete logarithm problem in the group. And because of certain property, every groups have some different kind of things. So now let's back to the main problem. Why are discrete logarithm problem easy for some group? Is there any specific reason, or is that just the additive group modulo n? Why are some groups easy? Why are some groups hard? First, let's look at this field extension. Given a group G, if there exists a field extension that is extended from the G, then the discrete logarithm in G is just a multiplication in F. This is exactly the reason why the discrete logarithm problem in integer under addition is easy to compute, because we can just use multiplication to solve the problem. Multiplication is just multiple times addition, multiples addition. And if we have an addition, if we have a group and the group has an addition operation. If we can find multiplication, then we can solve the discrete logarithm problem easily because of a field extension. However, there's no guarantee that the multiplication in all fields are easy to compute. For example, I've just read a paper, not read a paper, I found a paper like some time ago. It's about the elliptic curve, So people actually found the field extension of elliptic curve that defines the multiplication in elliptic curve, the point multiplication in elliptic curve. So if this is easy to compute, then discrete logarithm is also easy to compute. But the problem is this multiplication is not easy to compute. It's also very hard. So, so it's just another thing to note on. But let's say if you really can find some field extension that is easy to compute, field extension of a group, then the discrete logarithm problem become very easy because of field extension. Yeah. And another thing on why discrete logarithm are easy is the isomorphism. Let's say if I have a group G and H, discrete logarithm problem is hard in G, but it's easy in H. But we know that there exists we know the isomorphism from G to H, then we can just convert the problem into H and we solve the problem into H and we just convert it back in G. Then we can solve the discrete logarithm problem. So isomorphism is also very useful in this case. Remember that I just mentioned that prime order, since all group with prime order are isomorphic with this. If a group has a prime order, then there must exist a group isomorphism between G and a prime order, an additive group. And we know that the additive group is very easy to compute the discrete logarithm problem. So if a group G has a prime order, and I can find an isomorphism to an integer pz, it means that I can solve this discrete logarithm problem easily. But with the same thing, there's no guarantee that we can find a group isomorphism fast. We might never find a group isomorphism, even though we know that there exists a group isomorphism. This is why elliptic curve is still secure right now, because elliptic curve is actually using most of the elliptic curve has a prime order, but we just really don't have the way to find the isomorphism to the additive group. But this is not the case for some elliptic curves, which one of it is the anomalous elliptic curve. So this anomalous elliptic curve is the elliptic curve, but we can easily find a group isomorphism to the integer under addition. Yeah. And the last thing on why some discrete logarithm is easy is because of the smooth order. If G is an abelian group and the order of G is smooth, then the discrete logarithm problem in G is easy to solve using Polit-Hellman algorithm. What do you mean by a smooth? By smooth, a number is said to be smooth if the highest prime factor. So let's say if I have this is n1 or something like that. The highest prime factor of the number is small, means that the highest p is small, then the number is smooth. If the order is smooth and it's an abelian group, then we can solve it using Polit-Hellman algorithm. Yep. And boom. Okay. So that is all for my part. Now I will leave the rest to Alissa.
Oh wow. Okay.
Okay, you can continue on your sharing, I think.
Oh.
Or you just want to use my yeah. Which do you prefer? Do you want to share or do you want me to continue sharing and click the slides for you? Hello.
Oh, okay. Hello.
Yeah, so do you want to share yourself or do you want to use the
You can click for me, yeah.
Okay lah, then I click for you.
Okay, so for Divi-Hellman key exchange, let's just use the general as usual, Alice Bob. So there are two parties, Alice Bob, who wish to exchange a shared key through a public channel. So first, Alice Bob agree on a group G diamond and a generator G, which is a member of group G, and function F that maps the group element to the set of keys. And so Alice generates a random secret A and send A, which is equals to G to the power of A to Bob. Then Bob generates a random secret B and send B, which is G to the power of B to Alice. And then Alice gets the shared key by computing F big B to the power of A, and Bob gets the shared key by computing F A to the power of B. Since B to the power of A is equals to A to the power of B, which is equals to G to the power of A times B, Alice and Bob will get the same shared key. And then the security of this key exchange depends on the hardness of discrete logarithm problem in group G. And after exchanging keys, two parties can now communicate securely by encrypting or decrypting the messages using symmetric encryption systems such as AES through an unsecure channel. Some examples is like in group integer modulo 13 under multiplication, where G is equals to 2. As you can see, Alice has A equals to 5. Then big A is 2 to the power of 5, which is 6 mod 13. Then for Bob, where B is equals to 7, then big B is 2 to the power of B, which is 11 mod 13. Then Alice send A to Bob, and Bob send B to Alice. And then Alice will have S, which is B to the power of A, which is 7 mod 13. Then Bob will have S also, which is A to the power of B, which is equals to 7 mod 13. It's quite similar for the second example, which is when it's a group of integer modulo 23 under multiplication, where G is equals to 2. So yeah, Alice has A equals to 14, and big A is equals to 2 to the power of 14, which is 8 mod 23, and Bob has B equals to 5, and B is equals to 2 to the power of 5, which is 9 mod 23. Then Alice send A to Bob, and Bob send B to Alice. So both Alice and Bob will have S. Alice has B to the power of A, which is 16 mod 23, and Bob will have A to the power of B, which is 16 mod 23 also. So the next application is Elgamal encryption. So yeah, same kind of like the key exchange previously. Then for this one though, so Alice and Bob agree on a group G diamond and a generator G, which is a member of the group G, and a budgeting function F that maps the message to a group element. So for the encryption part, Bob will generate a random secret B and send B, which is G to the power of B to Alice. Then Alice generates a random secret A and computes A, which is G to the power of A, and S equals to B to the power of A. Then Alice maps the message M to a group element by using the function F, which is GM. Then Alice computes K, which is GM diamond S, and sends AK to Bob. And for decryption, Bob will just compute S, which is big A times to the power of B, and GM, which is K diamond inverse of S. Then Bob will decrypt the message by mapping GM back to M using the inverse function. Then elliptic curve cryptography is based on the group structure of elliptic curve over finite fields. And some properties are for the DV-Hellman key exchange and Algama encryptions. They are both applicable with elliptic curve group. And it offers a better bit security compared to multiplicative group modulo n. And discrete logarithm is hard in well-designed elliptic curve parameter, and it is widely used in modern cryptography and mathematics. And the rest are just some resources. Yeah, thanks.
Yeah. So that just So that's it for So now some challenges based on this group theory in cryptography. Okay, the first one is poly ISA. So basically what I have done is the ISA is like A to okay, so ISA is like m you raise to the power of e is equal to c, right, and mod some big N. So what I did is that I replaced this m with a polynomial. And if I replace this m with a polynomial, this I also replace to a polynomial. And this I also replace with a polynomial. And now this is the challenge. So I say with polynomial. Okay, so this is the first challenge. And then the second one, which is a diagonal. This one actually has some more bugs that I haven't fixed. So I will not post this challenge soon. I'll post it maybe after I fix the bugs. So basically what I did is that I define a matrix group. Okay, I define a matrix group, n times n matrix group. And I want you to solve the discrete logarithm problem in this matrix group. Yeah, so maybe I call this a G. Yeah, I'll call this a G. Call this a G. And this G I raised to a power of B. And yeah. I want you to solve discrete logarithm in matrix group. But how can we solve it? Is discrete logarithm easy in matrix group? Is it easy, or it has some certain properties that makes it easy to solve or not? Yeah. So but this challenge is not completed yet, and I will post the challenge later on. For now, I'll just post the first one in Discord. Okay, and that will be the end of our presentation. Any questions or anything else?
Hey, thanks. Thanks for very detailed tutorial to theory. I have a question for the discrete logarithm. Actually, all the others, other examples or applications you mentioned. So normally in maybe the most basic CTF challenges, we see Diffie-Hellman key exchange. You just take the numbers and you put into some online solver like Alphatron and you get the solutions, right? But are there any other examples that use different groups rather than just a very basic group of integers?
Previously in the Bamboo CTF, right? They introduced a new group. So the group operation is integer under XOR. And this integer under XOR, there actually exists another multiplication field extension. There exists a field extension of this group. So I guess that is a kind of a good example of defining a new group for CTF challenges. So this is the challenge that I faced just last time during the Bamboo Fox CTF, and then the challenge is coded using Pascal, and people are really mad about it. Yeah, so they define their own hash function and own encryption method, but it is not encrypted using discrete logarithm, but it is encrypted using some kind of other group properties. But it's one of the example that they use another group to construct a CTF challenge. So yeah, I think if you want to do something like create your own crypto kind of stuff, people usually do on group theories, because group theories are very interesting to do this kind of stuff in crypto.
Oh, okay, okay. Thanks. Then how about in real life? Or what do they normally use?
In real life, usually right now they just use elliptic curve and the usual Diffie-Hellman and key exchange using integers. And because they want to try to I think just these two lah. And if the most applicative part of this group theory is basically just elliptic curve, I think, because elliptic curve, they have a lot of some attacks that use advanced group theories and all that. So if you understand group theory perfectly, then you can solve this CTF challenge about elliptic curve also.
Okay, so we look forward to part 2. Either by you or by Anaf and Shihao.
Kel Zin, I have a question. So RSA and elliptic curves, right? They are both PKC that use group theory and algebraic structures. But from what I understand, elliptic curve is a lot more secure in terms of effective key length. Is there any specific property of elliptic curves that make it so much more secure than RSA?
The main reason is because it's not numbers. It's not just numbers. Because if we just RSA is you just take number to some power, right? And this number to some power is very predictable. And not predictable, but you can have some more things about it. But elliptic curve, you define a point in the plane, and the group operations are not really easy also. So the groups are a little bit complicated because of the complication of the groups. It's not easy to find some exploit or just some attack due to the complexity of it. Yeah. So
it's our hardware is more geared towards integer manipulation. That's why it's harder, is it?
No, our mathematics is because of mathematics. Hardware is elliptic curve is actually faster in hardware because of the shorter bit length. And this kind of few multiplication, few arithmetics is also quite fast in hardware. Yeah, this polynomial additions and all that. Yeah.
Then in practice, is the key space normally roughly the same order of magnitude for RSA and elliptic curve?
Usually it depends. I think if you want 512 bit security, then elliptic curve you will use something like 1024 bit security. But if you want the same amount of security for RSA, then you need to use something a lot larger. I think it just depends on how much security you want to use in the end. How much bit security you want to use in the end.
Okay, thanks.
So can we say that for this kind of crypto attacks is sometimes about thinking how to find the isomorphism, the additive integer?
Yeah. Some attacks are based on that, but they can be some more different kinds of attack, like some brute force attack or some in the middle attack or something else. But usually, if you can find a group isomorphism, it's definitely good. But it's not easy to find, and people usually dedicate a paper for some isomorphism, I think. So, yeah. Yep, side channel attack is very cool also.
Yeah, some recovery.
Yep.